Hi everyone, and welcome to our presentation on the Quaternary history of Northeast North America. We'll be dividing our history into 3 sections, so we figured we'd outline the terminology of each. The early Quaternary spans from 2.58 million years ago to 0.85 million years ago and coincides with the first half of the pre-Illinoian stage. The middle Quaternary spans from 850,000 years ago to 100,000 years ago and includes the second half of the pre-Illinoian and the Illinoian stage. And the final section, the late Quaternary, spans from 100,000 years ago to 14,000 years ago and includes the Wisconsin stage. And so the ice sheet that we're going to be discussing over the course of this presentation is the Laurentide ice sheet. One thing that's interesting to note about this graph in general that we'll be discussing throughout the presentation is that most records of glaciations come from more recent stages, not only because earlier glaciations are harder to date, but also because recent glaciations were more extensive. To give some context before we start talking about the Quaternary, during the Gauss-Krone, during the Pliocene, there weren't any glaciations in Northeast North America, even though you can see the Quaternary ice sheet it exists on the west coast of Canada. So the early Quaternary lasted for 1.7 million years ago, but we don't really have very much information about this period of time because subsequent glaciations during the Brunskrone extended beyond the Matuyama-Krone. But what's interesting to note about these reconstruction graphs is that there was initially a gap between the eastern Laurentide ice sheet and the western Cordilleran ice sheet. And even kind of in the upper Matuyama, you can see the gap beginning to close as the Laurentide ice sheet kind of expands further west. And given that the Cordilleran ice sheet existed before the Quaternary and that it remained more stable in size, it seems like the Laurentide ice sheet kind of grew much more and much more quickly to cover the gap between the 2 ice sheets. And then another thing that I found interesting about the Laurentide ice sheet during this time was that it was able to reach pretty far south without extending as far east or west as it would later in the Quaternary. And so we're going to talk about this region circled in red on the next slide. This is a really unique study that I came across where the researchers were able to collect till from the Matuyama-Krone. And so this is an area in the central Midwest that I circled on the previous slide. It includes Iowa, Missouri, Nebraska, and Kansas, where the last glacial maximum didn't reach as far as the ice sheet did in the Matuyama-Krone. And so if you look at this first figure, the map of the area, you can see the last glacial maximum in dark gray and the pre-Illinoian till in the light gray. So the till that we're discussing from the Matuyama-Krone is actually below the pre-Illinoian till. And so researchers were able to distinguish till layers from sedimentary column samples because of their distinct composition and polarity. And so if you can look at the second figure in the proposed sedimentary column, they separated the till into N, R1, and R2 till layers. The N stands for the normal polarity of the Brunskrone and includes the pre-Illinoian till. The R stands for the reverse polarity of the Matuyama-Krone, and they separated the R1 till from the late Matuyama and the R2 till from the early Matuyama. And so they were kind of within the R1 and R2 till able to kind of locate 2 distinct advances for each section. And so even though there were probably more than 4 advances during the Matuyama of the Laurentide ice sheet, it's still really cool that they were able to kind of take these till samples of a time that's so hard to get records for.
Great. And these global reconstructions of glaciations in the early Quaternary and the mid-Quaternary kind of like put what we're discussing into a larger context. So as you can see, the Laurentide ice sheet during the mid-Quaternary was much larger than it was during the early Quaternary. And this makes sense based on the larger trend of increase in volume, in the ice volume, from the early Quaternary into the mid-Quaternary. And so ice sheets reached their maximum extent during the mid-Pleistocene glacial maximum. So the mid-Quaternary can be said to have begun with the last geomagnetic reversal around 780,000 years ago. So sometime around this period, the behavior of the glacial interglacial cycles changed in what we know as the mid-Pleistocene transition, which is said to have occurred somewhere between like 1.25 and 0.7 million years ago. So this transition was characterized by a change in the length of periods between glacial cycles from 41 in the early Quaternary to 100,000 years during the mid and late Quaternary. And so our first discussion question, which we'll also ask again later, is what is a potential explanation for why that shift may have occurred? So if your answer had something to do with the Milankovitch cycles, so if you talked about those, good job, and you can go to the next slide. But researchers still aren't really sure exactly what caused like the change in the length of the period cycles. And they're also not really sure why glaciation reached greater extents after the mid-Pleistocene transition. So we note that in the mid-Quaternary and the late Quaternary, there's a general like great increase in global ice volume. And so Willett and al. Tried to answer those questions by running simulations that modeled the relationship between glaciation, climate, and the carbon cycle over the past 3 million years. And they found that in order for the climate to change the way it did, two things had to have occurred, which were, number one, a gradual decrease in atmospheric CO2, and number two, something called regolith removal. So regolith, which personally, that's a word that I had never encountered before. It's a layer of unconsolidated rocky material that covers the bedrock. And so the researchers in this paper think that before the Quaternary, all of like the northern hemisphere continents were covered in like a pretty thick layer of this like unconsolidated rocky material called regolith. And over time, as a result of glaciation, the glaciers like gradually eroded away this regolith, which actually changed the responses of the ice sheets to orbital forcings. And so one way that that happened was that ice sheets move at a faster velocity over a thick layer of regolith than they do over exposed bedrock. And so that means that when there's a lot of regolith, the ice sheets are more mobile and also more susceptible to orbital forcing. So when less regolith was present, because some of it had been eroded away by glaciers, the glaciers became less vulnerable to changes in solar forcings, and northern hemisphere glaciation became more persistent.
So here is the Laurentide ice sheet during the late Quaternary. As you can see, it covered not just Northeast North America, but also all of Central North America as well. So the late Quaternary, also the Wisconsin stage, spans about 86,000 years and is subdivided into 5 MIS stages. This figure shows MIS stages 5 through 1. The axes are time before present and watts per meter squared, which is a measure of solar radiation. The data was taken on the northern 60-degree latitude in Canada during June. The periods with higher watts per meter squared values are interglacials and interstadials, while the lower periods are glacials and stadials. For MIS 5D stadial, you can see that North America hit the lowest level of solar insolation, which makes sense because it coincides with a global increase in ice volume. MIS 5 ended with an interstadial leading off into the transition into MIS 4. MIS 4 is not super interesting, but one fun tidbit about it is that it wasn't as cold as MIS 2. So the Laurentide ice sheet was more warm-based in MIS 4 than it was in MIS 2. And so MIS 3 is a minor collapse of the ice sheet during this interglacial. It also marks the start of Heinrich events, which is when large icebergs break off from the glaciers and travel into the ocean. the Heinrich events marked at the top of this figure as H events lasted into MIS 2 and 1. So MIS 2 started with a very quick regrowth that expanded beyond the previous late Pleistocene glaciations, and then finally MIS 4 marks the final deglaciation of the Laurentide ice sheet. So this is a really pretty map that tracks the retreat of the Laurentide ice sheet during the late Wisconsin and Holocene during MIS 1. What's really cool about this map is that it shows that glacial retreat happened asymmetrically. The Laurentide ice sheet retreated much quicker in the west than it did on the east, which kind of makes sense given that when the Laurentide ice sheet was first advancing, it advanced more to the south and southeast before it moved west. The other interesting tidbit is that deglaciation happened really slowly for the first 4,000 years. You can see in the light blue section on the edges is kind of the retreat that took for the first 4,000 years. And then kind of marking around 14,000 years ago, the bed of the glacier changed from cold-based to warm-based, and it shrunk much quicker. So the retreat of the kind of second seafoam green section and the teal section also happened in 4,000 years, which shows just how much faster it deglaciated after that switch from cold-based to warm-based.
All right, and now we're going to move into some of the case studies that we read. So to start off with a little bit of geomorphology, I read a case study about the morphology and sedimentology of something called de Gruyere moraines on the New Hampshire seacoast. And so de Gruyere moraines, as you can see on this image at the top, are swarms of consistently spaced ridges that are usually less than 10 meters tall and less than 50 meters wide. They're only in coastal zones, and researchers think that they're the result of glacial recession in shallow marine waters, but researchers still aren't exactly sure how they formed. And so this is the location of where the study took place. So as you can see, by the biggest red area is Durham, New Hampshire. So that's kind of like the area that we're talking. And yeah, that is where they had their study sites. And so the researchers were asking a couple of key questions. Number one, how did these moraines form? And number two, what does this tell us about glaciation during the last glacial maximum in New England? And so they had three hypotheses for how the de Gruyere moraines form. The first is annual winter readvances. So as the ice front advances every winter, the front pushes sediment towards the margin. And in the summer, the ice retreats by calving. So the next winter, the ice sheet advances a little bit less and forms a new moraine. So you can see that in the first column. The second hypothesis relies on the glaciers pushing sediment into basal crevasses or transporting sediment via meltwater into moraine ridges. And the third hypothesis is that moraines form at the grounding line during pauses in deglaciation, and then as the ice sheets calve, sediment accumulates at the grounding line because of advection. So the same process would occur at every pause in deglaciation. So the researchers used two key methods for the study. First, they used sedimentology. So they were analyzing the till fabric of the pebbles and the sediment that made up these moraines, and figuring out where the sediment came from and how it was deposited, and what that said about the amount of energy that was there at the moment. And they also used LiDAR to create a very detailed relief map that computed average dimensions and distributions of moraines throughout the area, so they could get a better picture of what the moraines looked like. And so this is a picture of some of the LiDAR images they generated, as well as a cross-section of what the sediment looks like inside these moraines. And so they kind of broke it up into a couple of layers. The top layer, section number 4, being agricultural soil. So that's all anthropogenic in origin. and the next couple of layers are deposited by glaciers. And so what they figured out is that the sediment probably accumulated during seasonal readvances, and they found shearing in some of the clasts, which supported the theory that the ridges were being pushed forward by a readvancing ice front. You can go to the next slide as well. But the results were not totally conclusive. So while they found support for the first hypothesis that of the annual winter readvances, like pushing forward the ridges, they also found a little bit of evidence for the other two hypotheses as well. And one interesting thing is that they found that like the formation of these moraines supported an ice recession rate of about 100 meters per year. So like every winter readvance was like 100 meters further back than the last one, which is like really similar to what rates in southern New Hampshire were calculated from Lake Barbs. So that's kind of interesting. And then Anna will talk about our next case study.
All right, so for our second case study, I'm going to be talking about this really cool feature in Michigan that formed during MIS stage 2. In this study, the researchers Schetzel and Foreman used OSL dating to establish a regional chronology of glaciation. This is the location of the study in the high plains of northern Michigan, and the feature we're going to be talking about is the Grayling Fingers, which are 4 flat-topped ridges around 1.5 to 3.5 kilometers wide and 40 kilometers long. And they've been kind of incised to a height of 30 to 60 meters. The composition of the Grayling Fingers is what makes them interesting. They're composed mainly of outwash sediments with a small layer of till soils and a discontinuous silty cap on top. From the base of the fingers, the glaciofluvial outwash is about 50 meters thick, followed by the Blue Lake till about 10 meters and a single meter layer of the silt cap. And this is a pretty cool map of where you can find these deposits. So the formation of the sediments kind of help us understand how the Grayling Fingers formed. And the theory behind the Grayling Fingers is that for most of MIS2, they would have been an interlobate of the Laurentide ice sheet between the Lake Michigan lobe and the Saginaw lobe. The high plains of Michigan, where the Grayling Fingers reside, are, as you may expect, at a higher elevation. So it makes sense that they would have been unglaciated for most of MIS2. And this ice marginal position also allows for the deposition of the large volume of coarse glaciofluvial sediment present in the region. However, the region was eventually glaciated, leading to the deposition of our Blue Lake till. Finally, in the process of glacial retreat, meltwater incised into the Grayling Fingers into the ridges that we see today. And Schetzel and Foreman used the formation of the fingers as well as OSL dating to establish a regional glacial chronology and apply that to the dating of the last glacial maximum. So they used OSL dating on 10 outwash sediment samples from 3 locations, the Waters gas station, the Waters landfill, and the Oakville cemetery. What OSL dating of these sediments represents is the time of ice advance onto the Grayling Fingers, because that's when they would have been buried under the glacier and the Blue Lake till. And so they used the OSL ages and made this graph using probability density and found that the mean age of the sediments was about 27,000 years. So we've already discussed what our first main takeaway is, which is that ice advanced onto the Grayling Fingers 27,000 years ago, and this will lead us to our next takeaway. Schetzel and Foreman hypothesized that the Grayling Fingers may have been one of the last parts of Michigan to be glaciated. They suggest that the glacial advance onto the Grayling Fingers either happened simultaneously or before the Laurentide ice sheet reached its late Wisconsin margin. So this sets a bound for the estimate of when the Laurentide ice sheet reached that margin, because it couldn't have happened any earlier than 27,000 years ago. So to complete the kind of glacial chronology of this region, we also know from an earlier study that the high plains were completely ice-free by 15,000 years ago.
Sweet. And then our next case study, which is also a little bit about sediment, is the mineralogy and the provenance of the Pleistocene outwash on modern beach sands of Cape Cod, Massachusetts. So if you're familiar with, hold on one second, I'm gonna edit this part out. Anna, what do you want? Sorry about that. We will edit that bit out. Yeah. Okay, so if you want to go to the next slide, shows that the researchers focused on 4 outwash plains and beach areas that are identified on this map, which are all located on outer Cape Cod. So if you can see, like the ones outlined in red are the 4 outwash plains that the researchers focused on, as well as a couple of beach areas. And so the researchers asked a couple of key questions. Number 1, where do the sands on Cape Cod beaches come from, and like what are the pre-glacial sources? Number 2, do the sands of the 4 outwash plains differ significantly in mineral composition? So are they all from the same source, or did they come from different sources? And does transport produce significant changes in the composition of the sand? So the researchers collected sand from the 21 different beaches that were identified on the map, as well as the 4 outwash plains, and then figured out the mineral components of each. And so this was done in order to figure out the provenance of the sand, because the researchers essentially wanted to map the sands to their sources through their unique mineral compositions. And they also figured out the grain size distributions using sieves. And this allowed researchers to gain clues into how the sands had formed and how they were deposited. And basically, yeah, this shows kind of a breakdown of the types of minerals that make up sands at a couple of different outwash plains and beaches. And so they're kind of dominated by tourmaline, but have a couple of different types of minerals that dominate as well. And they're pretty similar, but not identical in composition. And so the researchers kind of, there is a lot of information already that the researchers like built upon in figuring out like what the origin story of these sands were, going like all the way back to like the like Cretaceous period, like way before any glaciation, when like some of these sediments like began to form. And so the researchers like used that information and built upon it to figure out like what happened after that. And so they concluded that during the Pliocene and early Pleistocene times, regional uplift and or a drop in sea level exposed the floor of the Gulf of Maine. And so streams that were flowing on the Gulf of Maine, which was not a sea, but on land, left like an incised stream channel network. And then during Pleistocene glaciation, ice covered a lot of the Gulf of Maine, and the glaciers carried something called like quartz rose sand, which was deposited in the till and the outwash. And then when the sea re-advanced after the mid-Pleistocene glacial maximum, those deposits were like moved around a little bit. They were moved and reworked. And then after that, the Wisconsin ice sheet advanced to its maximum, and that same quartz rose sand, as well as lithic pebbles, were transported by streams from the melting ice at the lobes of the glaciers to be deposited in the outwash plains that the researchers looked at. And then finally, after glaciation, the post-glacial rise in sea level modified the sediment, and currents that like run along the shore of Cape Cod transported sand and pebbles from the outwash plains onto the beaches. And that's why we see a similar composition in sands on the outwash plains as well as the beaches. Okay, and then for a final bonus case study, I decided to look at some of the evidence of glaciation that is around me in my neighborhood, which is in Lexington, Massachusetts, just outside of Boston, because I know that there was glaciation here, so I figured that there is probably evidence of it. And so there's this little tiny hill that's in my town. It's like barely like 300 feet tall, so not exactly a mountain, but it does have like a little bare peak. And so I was wondering, how did this hill, known as Whipple Hill, form? And I had two theories going into this. Number one, that it was a drumlin, which is a glacial depositional landform that is kind of a common feature of the area. I know that there are a lot of drumlins around where I am in like neighboring towns, and these hills are made mostly or entirely of glacial debris. So they have like these little shapes, and they kind of look like a school of fish. And then the second theory is that it was a roche moutonnées, which, as we learned about in class, is a glacial erosional landform where the glacier like smooths one end of the hill and then plucks away at the face as it like descends. And so I won't go into explaining that since we've like already learned a little bit about that. And so I went on a little tiny hike to the hill, nothing impressive. It's literally like 0.1 mile to the peak. And I took some pictures of what it looked like at the top. And as you can see, like this is bedrock, which made me think that the hill is an erosional feature rather than a depositional feature because of the fact that you can see the bedrock. And this is a picture of the south side of the peak of the hill. So I imagine that the ice would be flowing from north to south. And so that if there was like a plucked face, it would most likely be on the south. And you can kind of note like the roughness and the sharp angles of the rock, which I think maybe could have been plucked by ice flow. And then the north face was a little bit smoother than the south face. But also I kind of took these photos a little bit in a manipulative way. So there was like a little bit of difference between the smoothness and the roughness of the north and south faces, but it wasn't as clear cut as these pictures make it seem. And so my hypothesis is that this is an erosional roche moutonnées landform, but I could also just be making that up. Okay. Yeah, that leads us to our conclusion. Evidence of glaciation can be found in your own backyard.
We learned that the Laurentide ice sheet was very dynamic, and that it grew and shrunk over time in a lot of very interesting ways that kind of impacted the landscape clearly all around us.
Sweet. And then that leads us to our discussion questions. So the first one we talked about previously, but we just want you to explain why the time period between the glacial stages changed from every 41,000 years to every 100,000 years around the mid-Pleistocene.
And then our second question is to pick one case study and explain a way in which it tells us something about Quaternary glaciation in Eastern North America and how.
And then finally, we would love for you to pick one thing that you found interesting in our presentation that you want to learn about more. Sweet. Well, that's it. Thank you so much for watching. I'm going to end recording now.
Awesome.